Our universe is like a giant highway, and galaxies are constantly moving along this highway. And just like cars driven by careless drivers, they can collide and crash. So, astronomers have recently witnessed such an incredible cosmic collision. It involved galaxies traveling at incredible speeds. Using advanced instruments, researchers clocked one galaxy traveling at a speed of around 2 million miles per hour as it crashed into a group of other galaxies. This collision has created shock waves that are so powerful they can completely reshape the entire region, leaving long-lasting effects on its structure and dynamics. Will it somehow influence our solar system? Before we find out, let's learn more about the region where this collision occurred. Actually, this collision is still happening in Stephan's Quintet. That's a fascinating cluster of galaxies that has been the subject of study for scientists for over a century. It's a group of 5 galaxies located in the constellation Pegasus. This group of galaxies was first discovered in 1877 by the French astronomer Édouard Stephan, who used a telescope at the Marseille Observatory. Despite its tranquil name, Stephan's Quintet is anything but peaceful. It's a chaotic spot filled with galactic collisions and turbulence. 4 out of the 5 galaxies are gravitationally bound. It means they are physically interacting with one another. Such interactions are ejecting material from the galaxies, and over time, it forms vast debris fields in the space surrounding the galaxies. Astronomers believe that, in the end, these galaxies will merge into one giant galaxy, but it will only happen in millions of years. The curious thing, though, is that the 5th galaxy in the quintet, located in the upper left corner of images, is not part of the collision. This galaxy is much closer to Earth, more than 200 million light-years closer, to be precise. So its alignment with the other galaxies is just a chance perspective from our vantage point, making it appear as part of the group. Stephan couldn't know this in the 19th century, so the name quintet has remained, even though only 4 galaxies are physically involved in the collision. Now, how about we look at this collision in detail? At the center of this event is one of the galaxies in the group, which is currently crashing into the others at a breathtaking speed. From our perspective on Earth, this galaxy appears to be approaching the quintet from behind, heading directly toward the viewer. The collision is creating a massive shock wave that ripples through the surrounding galaxies. As the shock wave is moving through packets of cold gas, it's traveling at hypersonic speeds, several times the speed of sound in the intergalactic medium. This process strips electrons from atoms, leaving behind long trails of glowing ionized gas. But when the shock wave comes across regions of hot gas, it compresses the material rather than disrupting it. This compression produces radio waves, which can be detected by radio telescopes. While reshaping the structure of the intergalactic medium in Stephan's quintet, this shockwave also influences the future evolution of the galaxies involved. Now, how did scientists even manage to spot such a dramatic space event? All thanks to innovative technologies. The most important participant was WEAVE, a cutting-edge spectrograph that's installed on the William Herschel telescope in La Palma, Spain. This tool specializes in gathering spectroscopic data, which is the information about how matter absorbs or sends out light and radiation. It allows astronomers to examine the movement and composition of space objects with great precision. Besides WEAVE, researchers have used data received from a few other large observatories. One of those was LOFAR, Low Frequency Array. It's a radio telescope with an antenna network observing the radio waves the weaker shock wave produced while compressing hot gas. Astronomers combined the data received from all these instruments and managed to study the shock waves and their effects in amazing detail. This collision in Stephan's quintet gives us a fantastic opportunity to find out more about the interactions between galaxies, which can influence the evolution of the universe. You see, when galaxies crash into each other, their gas and dust gets redistributed, and it can trigger the formation of new stars and even cause central supermassive black holes to grow. And if we talk about Stephan's quintet, the ongoing collision in this area helps us get additional information about the behavior of gas under extreme conditions. Now, at the same time, galactic collisions aren't as rare as you might think. They are common on a cosmic scale, and in the early universe, collisions occurred even more frequently because galaxies were located much closer together. With time, such interactions have played a key role in shaping the universe. Even our own galaxy, the Milky Way, has experienced tons of past collisions. We can see the evidence of such destructive interactions in the form of debris streams and disrupted star clusters within the galaxy. In fact, astronomers predict that the Milky Way will collide with the neighboring Andromeda galaxy in about 4.5 billion years, eventually forming a new, larger galaxy. Even though they're moving at incredible speeds, galactic collisions are super slow processes from our human point of view. While galaxies may travel at millions of miles per hour, the distances they cover are so vast that mergers take millions to billions of years to complete. Now, galactic collisions don't look like explosive crashes you might be imagining. Instead, they resemble when fluid merges. When two galaxies collide, their gravitational forces distort their shapes. They stretch and warp, and exchange their material, stars, gas, and dust. As a result, tidal tails, rings, and even bridges between galaxies form. One of the most famous collisions between galaxies is ARP 148. During this cosmic crash, one galaxy became shaped like a ring, while the other stretched in a long tail-like form. That's how powerful gravitational interactions between galaxies during collisions are. But however impressive intergalactic collisions are, collisions between neutron stars, those ultra-dense remnants of massive stars, are among the most energetic phenomena in the universe. Neutron stars are incredibly small and dense. Just one contains the mass of our Sun packed into an area the size of a city. When two neutron stars collide, they often merge to form a black hole, releasing immense amounts of energy in the process. These events produce gravitational waves, ripples in space-time, that can be detected by instruments like LIGO and Virgo, as well as bursts of light that outshine billions of stars. On Earth, the possibility of a galactic collision directly affecting us is extremely low. Luckily, the timescales and distances involved make such events harmless to life on our planet. However, smaller-scale collisions, such as an asteroid impact, are more plausible. Asteroid impacts have occurred in Earth's history, and the most infamous of them caused the extinction of the dinosaurs 66 million years ago. And while large impacts are rare, astronomers closely monitor near-Earth objects to protect our planet from potential threats. Now, while we're talking about space collisions, a question may arise. Can life travel between planets? This is the idea of lithopanspermia, the transfer of life between planets via debris from collisions. If an asteroid or comet hits a planet, fragments of rock could be ejected into space. If those fragments carry microbial life, they might land on another planet and seed life there. And guess what? According to experiments, certain super tough microorganisms like cyanobacteria could survive the harsh conditions of space travel, including radiation and re-entry into the atmosphere of another planet. In any case, lithopanspermia is still only a theory and a controversial one among scientists, but it doesn't make it less fascinating. It might eventually help us understand how life could have spread across the universe. But let's return to the ongoing collision in Stephan's quintet. By studying such events, astronomers learn more about how galaxies interact, evolve, and influence their surroundings. Hopefully soon, we'll find even more interesting facts about this process. Stay tuned. So check this out. Astronomers have discovered an exoplanet they're calling Super Saturn. It's got rings over an AU wide. An AU is the astronomical unit, the distance between the Sun to the Earth. That's an incredibly huge ring system, hence its name. Super Saturn is being called Mamajek's object after the astronomer who led the team to whom we owe the discovery. Professor Eric Mamajek of Rochester University in New York found Super Saturn while scouring through data downloaded from wide-angle transit observations. WASP is the acronym for Wide Angle Search for Exoplanets. It's an ingenious project developed in the year 2000 by astronomers at Queen's University in Belfast, Northern Ireland, and St Andrews University in Scotland. Using 4 telescopes, the CCD video cameras on the scopes record the slight dimming of starlight caused by objects passing in front of stars. This is called the transit method of exoplanet detection. So, for example, the planet Venus transits across our view of the Sun every couple hundred years. A black dot, the silhouette of Venus, is visible, crossing in front of the Sun as Venus passes between our line of sight and the Sun. This tiny eclipse causes the amount of sunlight coming to Earth to be reduced by a minuscule amount, also known as teeny tiny. The same is true for all the stars in the Milky Way that have planets going around them. Exoplanetary transits in front of stars must be in direct line of sight with Earth for the starlight to be dimmed. Such transits do not occur very often. That's why thousands of stars must be looked at simultaneously for as long of a duration as possible, between 4 and 8 hours a night. WASP was created to stare continuously at as wide of a range of stars as possible. Maybe one of them would show an exoplanet transit. That translates into a lot of data being produced, about 40 gigabytes per viewing session. Computer scientists at Leicester University in England developed a computer program to store the data and generate photometric graphs of the light intensity of each star. Open University, also in England, joined the WASP project, took this data, and made it available for research by astronomers worldwide. The graphs of the intensity of starlight show that changes in its brightness are called light curves. These graphs have 2 axes. One is in the timeline axis, the other one is the intensity of light. As the object, considered an exoplanet, though it could also be a brown dwarf star, crosses in front of the star, the timeline axis keeps track of how swiftly it is moving. It tells us how close the object is to the star, while the brightness axis keeps track of how much the starlight dims. This way, we can find out how large the object is. Now, obviously, big objects will dim the light more and be easier to detect. At present, Earth-based equipment is not sensitive enough to measure the dimming caused by planets as small as Earth. Neptune's size and larger ones are the limit for WASP. However, the James Webb Space Telescope, which is now in operation, has a much greater sensitivity and will be able to resolve the transits of Earth-sized exoplanets. Now, I know you want me to get to Super Saturn, but there's something else you should be familiar with before we get there. If the exoplanet has an atmosphere, or, in the case of Super Saturn, a ring system, the starlight from the star the planet is transiting will shine through the atmosphere or ring system, and that can be detected too. The light curve will show less dimming in the photometric data, because not all the starlight is being blocked. Some light is still getting through the atmosphere or rings. This is important because it gives astronomers a reading of the atmosphere. The James Webb Space Telescope is fitted with spectroscopes that can determine the gas content of the transiting exoplanet atmospheres: oxygen, methane, carbon, etc. The WASP project has been really catching on. There's a Super WASP project now consisting of WASP North and a WASP South. One looks at the sky above the northern hemisphere, the other looks at the sky above the southern hemisphere. There's also a Next Generation Transit Survey, NGTS, based on the WASP project. It's automated, so astronomers don't have to stay up all night sipping coffee, but they can if they want to. Located at the European Southern Observatory in the Atacama Desert in Chile, the NGTS scans millions of stars and has discovered over 100 exoplanets, down to a size as small as 3 times the size of Earth. NGTS has started a Planet Hunters Club on social media. Citizen scientists can search the online database of light curves and perhaps discover your very own exoplanet. What had been a strictly British effort started by 1 or 2 astronomers is now a worldwide phenomenon. With the ability to read the spectroscopic signatures of atmospheric gases during exoplanet transits, a new idea emerged: technosignatures. That is, specifically identifying gases in exoplanet atmospheres that are produced by civilizations. The James Webb Space Telescope can do this. Gases from pollution, such as chlorofluorocarbons (CFCs), can be seen spectroscopically if present. Tritium from fusion reactions, if they have them, can also be detected, along with heat patterns from cities on the planet's surfaces. Technosignatures is a recent concept that originated after the WASP project started. Who knows what it will turn up? Now let's get back to Super Saturn. The star that Super Saturn orbits is J1407, a small, dim, sun-like pre-main sequence star of the 13th magnitude. Huh? Well, the human eye can only see stars to about the 6th magnitude, and each magnitude is 2.5 times dimmer than the previous one. So it's not an exceptional star, just another telescopic star out there in the Scorpius-Centaur region of the night sky. J1407 is a young star that hasn't yet settled into its stable, long-duration phase. This is important because Super Saturn, officially J1407b, is showing signs of having a ring system in an early stage of development. Super Saturn's light curve was tucked away in the mountain of data from the Super WASP project. Professor Eric Mamajek and his associate Matthew Kenworthy of Leicester University studied the data thoroughly and produced a detailed report on it. Knowledge depends on good data. The horizontal axis of J1407b's light curve, the time axis, is what's causing all the hubbub. It took Super Saturn weeks to transit across in front of its parent star, 56 days to be exact. Planetary ring systems that we are familiar with in our solar system orbit right around the equators of the gas giant planets and are very thin, from only a few meters thick down to a few centimeters. In a telescope, Saturn's rings will seem to disappear when the planet is at zero inclination toward Earth. Saturn must be inclined at an angle in relation to Earth to see Saturn's beautiful ring system. It's something everyone should make a point of seeing: Saturn in a telescope. If Super Saturn's rings blocked most of the light from J1407 for 56 days, it means that the planet had to be orbiting at a steep inclination to its star. If it were at zero inclination, we wouldn't see the rings blocking any light. Therefore, the orbital time could be determined, 10 years minimum to 200 years if the orbit is highly elliptical. The superplanet itself is calculated to be 24 times the mass of Jupiter, which means that if it is gaseous, it could be a brown dwarf star. Super Saturn appears to have a Mars-sized object orbiting around it, because there is a huge gap in the rings that was most probably cleared out by a large object. The Cassini division in the rings of Saturn is where the moon Mimas has cleared out a path through Saturn's rings. The light curve of Super Saturn has only been observed once. All the exoplanet detection systems are keeping an eye out for it to come back around J1407. No one knows when that will occur. Some astronomers have suggested that J1407b is a brown dwarf star system in itself, merely passing in front of, but not connected to, star J1407. An orbital reappearance of Super Saturn would disprove that conjecture. The center region of Super Saturn blocked out all the light from its primary star. This is what indicates that the ring system is new and in an early developmental phase. Over time, the very dense ring mass close to the planet is expected to thin as all this matter gets absorbed into the planet or ejected into space. This is what has happened with our solar system's gas giant planets. The Mamajek object is a shocker. Never before or since has a light curve been detected like Super Saturn's. Super Saturn has added a new chapter to our understanding of the formation of ring systems. So, here's to you, Super Saturn. Hope to see you again soon. Now, scientists have a wild theory. What if our entire universe is actually inside a black hole? This is called the black hole cosmology. Some scientists have the idea that our observable universe and everything we see around us might be tucked inside a black hole, which exists inside another parent universe or even multiverse. And then this multiverse could be part of a bigger one, and so on, kind of like a stacking doll. Sounds like pure science fiction, but this is based on some curious facts. When scientists create the timeline of our world, they say that everything started from a singularity. If you kept squeezing a giant ball smaller and smaller, at some point it would get super dense before it crushed. Well, it's hard to imagine, but in space, it's possible to squeeze a crazy amount of mass into a teeny tiny point. This point is called a singularity. The matter gets crushed into an infinitely small space, less than an atom, and it holds all the same mass of everything, while taking basically no volume. Inside this singularity point, things get so intense that the normal rules of physics just stop working. Everything we know, time, space, matter, breaks down and can't be applied anymore. Basically, what happens from now on is beyond our understanding. So, scientists say that this was the starting point of our world. When the Big Bang happened, it's like this tiny dot with everything inside it expanded to everywhere. This started forming the universe as we know it. And here's the thing. Scientists assume that singularity also exists deep within black holes. General relativity says that a black hole is born when something really big, like a huge star, collapses under its own weight. Gravity gets stronger the bigger the mass is. With a mass of a huge star, tens of times bigger than our Sun, this tiny point would have an unbelievable gravity. It's why it starts sucking in all the stuff around it and curves the fabric of space-time so much it looks like a hole in space. And this would be the center of a black hole. It's a dot where all these things fall into and get crushed into an infinitely dense point. So, could our universe itself be just a little singularity dot inside a huge black hole inside of another universe? Well, that would be wild. So, it's not that easy to compress something so much that it literally warps space-time. You'd need to squeeze it like crazy. If you wanted to make a small black hole, like a human size, you'd need to shrink them down to the size of an atomic nucleus. If you want a black hole the size of a chickpea, you'd have to compress our entire planet to that. But our universe is 99% empty space. There are trillions of miles of just nothingness between the stars. If you were to pack all the matter in the universe together, the result would be surprisingly small. Everything around us, including galaxies, stars, planets, and dust, would only fill about 1 billion cubic light-years. It would be a cube about 1,000 light-years on each side. For comparison, our Milky Way alone is 100,000 light-years in size. That's how sparse the universe is. But at this density, it would also be very, very massive. The resulting mass would likely collapse into a black hole. And here's the wildest part. The resulting black hole would be roughly the same size as the universe itself. It would also have the same mass and energy, as well as the same average density. The size or radius of the black hole grows together with its mass. The more stuff it eats, the bigger it is. But the density works the other way around. The black hole gets less dense as it grows. For a size that big of our entire world, it would be pretty sparse as well. And it's not the only coincidence. We have this thing called the Hubble radius, also known as the cosmological event horizon. If we imagine our observable universe as a giant bubble, then think of its edge like the farthest part of the universe we can see. When you stand in a field and look around, trying to see as far as you can, your eyes will draw a circle. This is like that. There might be more beyond that point, but we'll never know. Beyond this horizon, the light from distant parts of the universe will never reach us. That's because light travels at a certain speed, and the space between us and those regions is expanding too quickly. It's like running towards something while super strong winds try to blow you away. Until we stay on Earth, we're cut off from those far-off corners forever. The black holes have something eerily similar called an event horizon, or the Schwarzschild radius. This is the point of no return. This is the imaginary line that's often depicted as a light contour around the black holes. Anything crossing an event horizon, falling inside, is lost forever. No light, no matter, no information can escape from there. Black holes' gravity is way too strong, so they're perfect space vacuum cleaners. And as we mentioned before, if we create a black hole the size of the universe, they would have the same mass and the same event horizon radius. Now, while some scientists think this could just be random coincidences, Others believe it's a clue that our universe might actually be inside a black hole. The theory also suggests that our universe might not be the only one. It could exist in one of many black holes scattered throughout a large multiverse. In this crazy model, each one of them, both in our world and our parent world, could lead to its own universe, with its own set of physical laws and structures. Now that would be some weird chain. There's this theory that says that universes could be born inside of black holes, sort of. It's called the Einstein-Cartan theory. This idea talks about singularity as well, but in a different way. It says that instead of collapsing into an infinitely dense dot, the matter might create a wormhole. This is like a tunnel through space and time. This wormhole, also known as an Einstein-Rosen bridge, could connect two different places of our universe. In that case, one side of the tunnel is the black hole, and on the other side, there would be a whole new universe forming. So it could work like a teleport. As soon as you pass the event horizon, you travel to the new world. But in that case, there should be an exit. Some scientists made it up and called it a white hole. It doesn't literally exist, not as far as we know, but it could be possible somewhere on the other side. It would serve as an exit of a wormhole, an area where matter is always ejected instead of pulled in. So it's like you can't throw anything in there, it would get expelled immediately. That's all purely hypothetical, of course. All this stuff fits well into the concept of the Big Bounce. This idea says that instead of our universe beginning with a singular Big Bang, it bounced from a previous state of collapse. Remember the squeezed ball analogy? Well, maybe there used to be another universe ball that got super compressed to a minimum size before rebounding and expanding again. So instead of a universe born from nothing, we might live in one that's a cosmic recycling of another. There's also another version of this theory, sometimes called shockwave cosmology. The idea says that the Big Bang could have been caused by a boom inside a black hole, and this could create the expanding universe we see today. As the universe expands and the matter density decreases, the black hole would eventually transform into a white hole, the reverse of a black hole, where matter is expelled instead of pulled in. But even though we have all these interesting connections, they're not evidence. There are no experiments or observations that could prove or disprove these wild theories. So they all remain speculation for now. But at least it's fun to speculate.
Saturn's iconic rings will disappear in less than 2 years. Soon, we won't be able to see Jupiter's Great Red Spot. Pluto's atmosphere might vanish any day now. Even the universe itself could be slowly evaporating right at this moment. But let me start from the very beginning. Saturn's rings won't vanish forever, at least in the near future, but they will seemingly disappear from view. This phenomenon is caused by the planet's tilt as it orbits the Sun. As a result, the eye-catching rings adorning the gas giant will get invisible to stargazers in 2025. This outrageous disappearance occurs because Saturn's thin rings turn edge-on. It's like holding a sheet of paper horizontally at eye level parallel to the ground so that only the edge of the paper can be seen. Something similar happens to the gas giant's rings. As the seasons on the planet progress, instead of the southern side of the rings tilted our way, we start seeing the northern side. But then the planet tilts again, revealing the southern side once again. Such a ring plane crossing happens every 15 years when our planet passes through the gas giant's ring plane. The last time this phenomenon occurred was in 2009. Afterward, the rings gradually became visible again over the course of several months. This time, the rings will be on edge in March 2025. Then they will slowly come back into view and disappear again in November of the same year. Soon after that, the rings will reappear, first becoming visible to the largest telescopes, later for everyone else to see. At the same time, further into the future, the rings might cease to exist for good. Astronomers have concluded that Saturn's rings, which mostly consist of ice and rocky dust from smashed asteroids, are younger than we thought. They're losing tons and tons of mass per second all the time, and it's likely to be a few 100 million years at most before they vanish completely. Let's move to the Great Red Spot on Jupiter. This immense raging storm might stop spinning in the next 20 years. The storm in question is larger than our planet. It was first spotted in 1830, but observations from the 1600s mentioned the presence of a giant spot on Jupiter too. If it was the same Great Red Spot, then we can say that the storm has been raging for centuries. The storm's vortex has remained so powerful thanks to Jupiter's 300 to 400 mile-per-hour jet streams. But like any other storm, the Great Red can't keep raging forever. It's been shrinking for a long time. In a decade or two, it's predicted to turn into GRC, the Great Red Circle, and who knows, maybe it will later turn into the GRM, the Great Red Memory. In the late 1800s, the storm was more than 35,000 miles across, 4 times the diameter of Earth. But when Voyager 2 flew past Jupiter in 1979, the storm had already shrunk almost twice its original size. And this shrinking is still happening. In 2017, the GRS spanned the width of a bit more than 10,150 miles, less than 1.3 times the diameter of Earth. Moving on, Pluto's atmosphere is going through a weird transformation. This icy dwarf planet sitting over 3 billion miles away from Earth in the region of the Kuiper Belt drew astronomers' attention in 2018 when it passed in front of a star. With such a powerful source of light illuminating Pluto, researchers managed to examine the dwarf planet and its atmosphere. They came to a shocking conclusion that Pluto's atmosphere is refreezing back onto its surface as the dwarf planet gets colder and colder. Astronomers used several telescopes in different spots in the USA and Mexico to observe Pluto and its thin atmosphere, which is mainly made of nitrogen. This atmosphere is supported by the vapor pressure of ice on the surface of the dwarf planet. For around 25 years, Pluto has been moving further away from the Sun, and its surface temperature has been gradually going down. Pluto is really far from our star at the moment, but at one point it will start getting closer in other regions of its incredibly huge orbit. Besides Jupiter's Great Red Spot, Saturn's rings, and Pluto's atmosphere, we're also losing stars. But stars don't vanish, right? For thousands of years, scientists believed that lights in the sky were fixed and unchanging. Even after they realized those lights were physical objects, just like the sun, they were still sure that stars went through major changes extremely slowly, on timescales of millions and billions of years. In reality, though, the most massive stars, which can be hundreds of times heavier than the sun, can go through sudden catastrophic events. For example, once they reach the ends of their lives, they pass away in blinding explosions of supernovae, shining for months on end and visible across hundreds of millions of light years. But there are stars that seem to just wink out of visibility. It should be impossible. And over the past years, a group of researchers tried to figure out whether there's actually a chance of such a phenomenon happening. They started to compare data collected over decades of observations. The project is called VASCO, the Vanishing and Appearing Sources During a Century of Observations. The scientists are interested in all kinds of disappearing objects, but they're hoping to find a star that was steady and present for a long time, and then just vanished without a trace. Even if you point a super powerful telescope there, you'll still see nothing. Our current understanding of space and its laws suggest that stars change very slowly over long periods of time. Dramatic disappearances are supposed to leave noticeable traces behind. Of course, it doesn't mean that all stars should shine steadily. The sky is filled with stars that change in brightness and pulsate. But VASCO is about something very different. They want to find something that goes from a completely steady star to vanishing entirely. Such a phenomenon hasn't been documented yet, and such a discovery might lead to new physics. And now, let's move on to the most disturbing part, the one about the evaporating universe. According to a famous theory proposed by Stephen Hawking, black holes, the densest objects in the universe, evaporate over time. They lose mass in the form of bizarre radiation. But a new study claims that Hawking radiation, or something very similar to it, might not be limited to black holes. It's likely to be everywhere. and it could mean that the universe is slowly but surely evaporating right in front of our eyes. Now, Hawking radiation is something no one has ever observed, but theories and experiments suggest that it can actually exist. Let's see how it works. There's a misconception that black holes are cosmic hoovers, slurping up everything that comes too close with the help of their immense gravitational pull. In reality, though, black holes don't have more gravity than any other body of a similar mass. What they're famous for is their density, incredible amounts of mass packed into a tiny, tiny space. Within a certain proximity to such a dense object, gravitational pull becomes so powerful that it becomes impossible to escape. Not even the speed of light in a vacuum is enough, and that's the fastest known thing in the universe. At the same time, anything massive or dense enough can produce a serious curvature of space-time. In simple words, the immense gravitational field of these objects makes space-time wrap around them. Even though black holes are the most extreme example, space-time also curves around other super-dense objects, like white dwarfs, and neutron stars or galaxy clusters. It means that any super-dense and supermassive object can have some sort of radiation similar to Hawking radiation. And after a very, very long period of time, it could lead to everything in the universe evaporating, following the fate of old supermassive black holes. If it turns out to be true, it will change our understanding not only of Hawking radiation, but also our view of the universe and its and our future.
A long time ago, we believed that the entire universe revolved around our own little blue planet. It's called a geocentric model. We thought that the sun, the stars, and all those twinkling celestial bodies all danced around us. This theory was super popular in ancient Greece and Rome. Famous geniuses like Aristotle and Ptolemy really loved this idea. Why did people believe this in the first place? Well, first of all, we have a massive ego. Second of all, there were a couple of things that seemed to support it. For example, if you stand on Earth and look up at the sun, it seems like the sun is spinning around us once every day. The moon and the planets seem to be doing the same thing. The obvious conclusion is, oh, they're probably twirling around the Earth. Then there's the fact that Earth feels pretty steady when you're standing on it. It just doesn't feel like it's moving, you know? And because of this stability beneath our feet, people thought that the Earth was unmoving. But even back then, there were ancient Greek and Roman philosophers that were onto something cooler. They paired the geocentric model with the idea that Earth was actually a round ball floating in space, not a flat disk. They started connecting the dots. And after a while, astronomer and mathematician Aristarchus of Samos had a game-changing idea. He thought that the Earth might not be the center of everything. He proposed that everything revolved around the sun. Funny to think that back in the days, this idea was considered insane. That's why for a while, most people stuck to their geocentric views. It took us many centuries to finally accept the heliocentric model, where all the planets in our solar system revolve around the sun. This idea was brought to life by people like Copernicus, Galileo, and Kepler. This change wasn't easy for people. It was hard to let go of our space crown. But gradually, we came to terms with it. And by letting go of this idea, we discovered a whole new world. This journey led us to an astonishing realization. Not only we're not the center of the universe, we're nothing but a little speck in it. We're a microscopic dot, sprawling galaxy called the Milky Way. The discovery of the Milky Way started right from our own backyards. If you've ever gazed up at the stars on a clear night, you might have noticed a faint, luminescent band stretching. It's like a shimmering celestial ribbon woven with stars. That is our galaxy. It was named Milky Way because it looks like someone spilled milk on a road. It was perfectly depicted in the 90s by Voyager 1. NASA's spacecraft took a picture called the pale blue dot. That tiny little pixel that's almost impossible to see is our planet. The photo was taken from a chilling 3.7 billion miles away from the sun. On a universe scale, this distance is nothing. But for us, it's unimaginable. So when scientists discovered the Milky Way, they armed themselves with telescopes. Their goal was to map the uncharted territories of the night sky. And of course, to find our place in this gigantic world. To do that, first, we had to unlock the secrets of our galaxy's structure. Okay, so we can clearly see that it has some band-like formation. That probably means that our galaxy is not a big, round ball, like the planets and stars. In reality, it's more like a giant pancake, a flattened disk. And we can see that we're not above it and not below it. We're right on the plate. The next step is to travel across the Milky Way to map it. There's a little problem, though. To do that, we'd have to traverse thousands of light years perpendicular to this pancake-like plane. Just to put things in perspective, think of Voyager 1, the one that took the pale blue dot picture. That spacecraft has been journeying through space for almost half a century. It left the solar system years ago. You know how many light years it traveled? 0.002. And how many light years is the Milky Way? 100,000. You get the picture. But the lack of fancy technology didn't stop us. In the 18th century, a bold astronomer named William Herschel decided to explore our galaxy. With nothing but a telescope, this Indiana Jones of astronomy started mapping the stars in the night sky. As a result, he discovered Uranus, more than 2,000 nebulas, and created the first map of the Milky Way that depicted it as a disk. The map wasn't super accurate, but still very impressive. Unfortunately, he didn't know about something called interstellar dust. It's like space fog that can block our view of stars in the center of the Milky Way. This dust made the central region of the Milky Way appear less crowded than it actually is. Now, let's go all the way to the 20th century. Henrietta Swan Leavitt, an American astronomer, was another curious stargazer. But she focused her attention on a special kind of star called Cepheid variables. These stars had a unique quirk. They pulsed, getting brighter and dimmer in a predictable pattern. Leavitt's job at the observatory was like being a librarian. She cataloged these special stars, and in doing so, she stumbled upon something incredible. A direct link between the brightness of these stars and the rate of their pulsations. This discovery is now known as Leavitt's law. It meant that by simply measuring how quickly these stars pulsed, astronomers could figure out how far away they were. These pulsating stars became the rulers for measuring distances. Before the 1920s, most scientists believed that our Milky Way was the only galaxy in the universe. But as telescopes improved, some astronomers started realizing that this isn't the case. We started finding more and more galaxies. But if the Milky Way was just one of many galaxies, where exactly were we within it? Meet the scientist named Harlow Shapley. Armed with a powerful telescope, Shapley turned his attention to globular clusters. These are tightly packed groups of ancient stars that gather together in spherical shapes. That's when he noticed something interesting. The oldest stars around us weren't scattered all over the canvas. They were clustered around the center of the Milky Way, and they were pointing in the direction of certain constellations like Sagittarius and Scorpius. It turns out that the origin of our galaxy began from the center. It was the heart of the Milky Way, and the most ancient guys were hanging out there, which means we're not even at the center of our own galaxy. Seems like our importance becomes less and less with each new discovery, huh? Anyway, Shapley found out that we were positioned somewhere on the outskirts of our galaxy. Shapley's calculations weren't perfectly accurate, but he got pretty close. Luckily, now we have very precise and cool tools. Since then, we've since pinpointed our precise location. We're located near a partial arm of the Milky Way called the Orion Arm. It's about 26,000 light-years from the heart of our galaxy. And that was the story of how we found out where we are in the Milky Way. You think our story is over? Oh, absolutely not. Meet Gaia, the European Space Agency's celestial cartographer. Launched in 2013, Gaia embarked on a daring mission. It has to map the Milky Way in unprecedented detail. Not just some rough map, but a photographer capturing every nuance of our galaxy. Gaia is piecing together the positions and motions of about 1 billion stars, and it's like 1% of the stars in the Milky Way. But even that tiny fraction is enough to create a masterpiece of cosmic cartography. What a grand journey it was. It led us from thinking Earth was the center of the universe to realizing we're less than a speck in the grand scheme of things. But what's more important is that this story shows humanity's drive to uncover the mysteries of the world. And there's always something new to explore. Discoveries just keep coming, so stay tuned and keep looking at the night sky.
Imagine a being so powerful it can suck in entire galaxies, so mysterious it's invisible to the naked eye, and so impressive it bends the very fabric of space and time to its will. Yes, meet my mother. Just kidding. Actually, meet the ultimate superhero of the universe, the black hole star. What is it and how does it work? Well, let's find out. The universe is full of marvels, and the black hole star is one of the most impressive ones. It's a supermassive force that can bend the laws of physics and a true enigma for scientists to unravel. No wonder science fiction writers find them so captivating. A black hole star, also known as a quasi-star, is a hypothetical type of extremely massive and luminous star that may have existed early in the history of the galaxy. They're predicted to be as luminous as a small galaxy, but unlike modern stars, they weren't powered by nuclear fusion in their cores. A quasi-star's energy would come from material falling into a black hole at its core. And yes, just like a normal black hole, these stars have the power to suck in anything and everything that gets too close, including stars, dust, and even entire galaxies. But how is it possible that the star is born from a black hole? And what's more, how do they continue to coexist together? Well, first let's discuss how black holes are born in general. It all starts with a supermassive star, one that is at least a few times more massive than our own sun. This giant of a star burns bright and hot, shining with the light of 1 million suns. But eventually, it runs out of fuel and its fate is sealed. As its lifespan comes to an end, it makes one final massive boom, a blast so powerful it can outshine an entire galaxy. This blast is called supernova. During this boom, the outer layers of the star fly away, while the core gets squished together by its own gravity. If the squished core is heavy enough, it can keep squishing until it becomes a black hole. And just like that, a black hole is born. Don't even try to put diapers on this thing. Now, this cosmic monster baby can continue to grow by swallowing up anything that comes too close, including stars, dust, and even entire galaxies. This is basically what's happening now in our universe with supermassive stars. But what about quasi-stars? The formation of a quasi-star could only happen early in the development of the universe, before hydrogen and helium were contaminated by heavier elements. And because of that, quasi-stars have one important feature. They are gigantic, so enormous that it's literally impossible to imagine. They may have been dwarfing even the largest known modern stars, like VY Canis Majoris and Stephenson 218. No wonder they're so scary. They were born from protostars, one of the first stars in the universe, the great-great-grandfathers of, everything. So now, imagine a protostar so massive that its core collapses into a black hole, just like we described before. But the key difference is that in a regular supernova, the outer layers of the star are blown away by the energy released during the boom. Meanwhile, in a quasi-star, these outer layers are massive enough to absorb the energy without being blown away. What do we get in the end? A star with a black hole in its core that weighs from 1,000 to 10,000 solar masses. This quasi-star is about 14,000 times bigger than our Sun, which makes them bigger than any star we know today. These celestial titans have some pretty crazy properties. Once a black hole is formed at the center of a giant protostar, it starts to give off a ton of energy. This energy helps to balance out the force of gravity, making it kind of a giant fusion-based star. They would be so bright that each one would look like a small galaxy. Quasi-stars would have a pretty short lifespan, around 7 million years. Just for comparison, our Sun is about 4.5 billion years old, and it's only halfway through its lifetime. But either way, during this short period, the black hole at the center would grow to be about 1,000 to 10,000 times the size of our Sun. Quasi-stars are also thought to be super hot, with temperatures reaching over 17,500 degrees. But as a quasi-star gets older, it starts to cool down, and its outer layers become see-through. Eventually, it cools down to a temperature of 6,740 degrees, and at that point, it's curtains for the quasi-star. It can't survive at that temperature, so it just dissipates, leaving behind an intermediate mass black hole. Unfortunately, right now, there's no observational evidence for the existence of quasi-stars. This is because they're thought to have only existed a very, very long time ago. They may have been very massive population 3 stars, which are extremely rare and difficult to detect. It's also very unlikely that any of them would still exist today because of their super short lifespan, only 7 million years. So why do scientists believe that quasi-stars could have existed? Because they're looking for ways to explain how supermassive black holes formed so early in the history of the universe. They're found at the center of most galaxies. But how could these monsters have formed so quickly? After all, it takes a really long time for small black holes to grow into supermassive ones. This is where the idea of quasi-stars come in. These stars aren't just destructive forces of nature. They're like the black belts in the martial art of gravity. They can bend and twist anything to its will. That's why these stars, if they really existed, had to play a crucial role in the evolution of galaxies. They must have been instrumental in shaping the universe as we know it. So, those intermediate-sized black holes that they left behind could eventually turn into supermassive black holes in the center of galaxies. But we're still yet to solve this cosmic mystery. Detection and study of black hole stars is like trying to find a needle in a haystack. Only instead of a needle, it's an invisible and mysterious object. And instead of a haystack, it's the vast expanse of space. But with the help of some pretty cool technology and a lot of brainpower, scientists are getting closer to uncovering the secrets of these celestial giants. Here are some things that can help us in this research. First of all, gravitational waves. They're like ripples in the fabric of space-time, caused by the movement of massive objects. Albert Einstein predicted them way back in the 20th century, but they were finally detected only in 2015. We caught them by observing the collision of 2 black holes. This discovery confirmed that black holes can merge and that they're a powerful source of gravitational waves. Scientists think that by studying these waves, they can learn more about how black holes form and grow. We can also try to detect quasi-stars by observing the effects of their gravity on nearby objects. It's like trying to spot a criminal by their fingerprints. For example, if a black hole is located near a star, scientists can observe the star's light being distorted as it's pulled toward the black hole. And of course, we can use our technologies, such as X-ray, infrared, and radio telescopes. This allows us to study black holes in various ways and at different stages of their lives. In other words, scientists are working hard to uncover the secrets of these celestial giants. We develop new telescopes, search for primordial black holes, and try to understand the connection between black hole stars and dark matter. And we're making some pretty incredible discoveries, just like with gravitational waves. All these things will bring us closer to uncovering the secrets of quasi-stars. And when we find out the truth about them, it will become a new page in our scientific history.
Empty space is not really empty. At least, that's what quantum field theory says. It's actually filled with tiny vibrations that can turn into virtual particles if they have enough energy. These virtual particles can produce packets of light with low energy called photons. Now, there's something every black hole has: an event horizon. It's a point of no return. That means once something crosses that point, it can never get away, not even light. And there's an insanely strong gravitational force around the event horizon. Black holes survive by gobbling up gas and stars around them. In most cases, a black hole has a swirling disk of material that surrounds it, called an accretion disk. It glows brightly as all those things that come too close to an event horizon get heated up and torn apart before the black hole swallows them all. As material comes closer, it starts to travel and move faster and faster, going all around the black hole. This makes the accretion disk glow and, at the same time, outlines the shadow of the black hole, which is basically the very event horizon we're talking about. Black holes might even want to hide, but they do so awfully badly. According to Einstein's theory of general relativity, gravity bends and warps space and time. It means that the closer you come to this extremely powerful gravitational pull around the black hole, the more twisted space and time around it become. That's what Stephen Hawking was talking about nearly 50 years ago, and it doesn't stop there. He also suggested that if these particles find a way to escape a black hole, they steal some of its energy. And because of these thieves, the black hole loses its energy as time goes by until it, at one point, completely disappears. He suggested that black holes release energy in the form of thermal energy or heat, which is called Hawking radiation. And this radiation doesn't carry any information. It means that when a black hole evaporates, it destroys all information it had about the star that created the black hole. That way, we can't know what really happened. And it's kind of confusing because the laws of quantum mechanics say the information can't be destroyed. This conflict is something we call the Hawking information paradox. According to Hawking, all this information isn't really lost, but is stored in a cloud of all those zero-energy particles that surround the black hole. He called that soft hair. Now, there's this new study as a possible solution to this paradox. Maybe Hawking radiation is non-thermal. Instead of just releasing plain heat, it's possible the black hole sends out a message in the form of radiation. This message contains important information about the black hole's past, the stars that formed it, and other details we thought were lost forever. It's like a secret code that tells us all about the history of the black hole. But let's go back to Hawking's theory, where a black hole can eventually disappear. It says that not only black holes produce Hawking radiation, any object with enough mass can. Researchers actually studied a process called the Schwinger effect too. It's when an electromagnetic field creates strong distortions and in that way forms matter. They applied this idea to Hawking's theory of black hole radiation. What they found is that the radiation Hawking predicted can actually be created in places with different levels of gravity, not just around black holes. Here's the key. When there are massive objects, like stars or planets, they create a curving effect on space and time. This curving is there because of their strong gravity. Even if you're far away from a black hole, there's still some massive object somewhere around that creates the curving of space, which can make you feel like you're in that twisted space. It can create radiation, similar to what happens near black holes. It means that not only black holes can slowly evaporate, other massive objects in the universe can also lose their energy in the same way. If this is true, the energy of everything in the universe will slowly be drained away in the form of light particles. That means everything and everyone, including stars, planets, black holes, and us, share the same destiny and will all eventually fade away. This sounds scary at first, but even if this theory is true, it's not going to happen anytime soon. It would take way longer than the current age of the universe for a supermassive black hole to completely disappear. So, in the way we measure time, black holes are basically eternal. And stars could last even longer since many black holes formed after some giant star collapsed upon itself. Some others belong to a group called primordial black holes. Hawking, who became famous for talking about black holes, mentioned those ones as well. And the theory says they probably formed spontaneously in the early universe, not long after the Big Bang happened. Hawking realized that primordial black holes could have different sizes, from very light to very heavy. Really small ones would have disappeared by now because of Hawking radiation. There's a pretty cool idea that these primordial black holes could be dark matter. It's a mysterious substance that scientists think exists in the universe. It doesn't give off or reflect light, so we can't see it directly. Scientists think dark matter might explain why stars and galaxies move in strange ways. But we still don't have the tools yet to confirm whether these black holes really exist, or if they're actually made up of dark matter or not. Hawking also explored the idea that our universe is just one of many universes. It's a concept called the multiverse. Some scientists believe it could be that any situation you can imagine in your life is happening somewhere in some other universe. Hawking didn't agree with that, so in his final paper, he proposed a new mathematical framework that made the multiverse finite instead of infinite. This means that there would be a limited number of universes rather than an infinite number. Another thing that's hard to test and prove, but at least he left us with something to think about. Believe it or not, time travel is not that impossible according to the laws of physics. Scientists have equations that suggest we could have something called closed time-like curves that might allow us to go back in time. Imagine going back to the most embarrassing moments of your life. Knowing what would happen, you could avoid them. But here's the tricky part. Going back in time could cause some big problems. It could create situations where things would happen in a way that doesn't make sense. Imagine you're walking down the street and meeting your younger or older self, or accidentally changing things that have already happened. Hawking was talking about this part too. And these are all things that made him concerned about time travel. He made a guess called the chronology protection conjecture. He suggested there might be a rule of nature that stops time travel from happening because it could create all these strange and confusing situations where we would just go back, fixing our wrong decisions rather than living in the present. Until we discover traveling through time without causing such disruptions, I guess all we're left with are life lessons and learning from our mistakes. In his last years, Hawking talked about the future of humanity, and we still don't know if he was totally serious. He mentioned a special particle called the Higgs boson that could cause a big bubble that could gobble up and eventually even destroy the universe. He also mentioned things like beings from other planets coming to Earth and conquering us, or robots becoming smart enough to take over the world. Some of his ideas turned out to be true, and time will tell if it will be the same with the others.
So, are you tired of boring old Earth? Want to know what lies beyond the starry night sky? You're not the only one. People have been asking the same question for centuries. Luckily, scientists have got you covered. They've discovered a lot of amazing places light years away from our blue planet. Just one light year is about 6 trillion miles. Mind-blowing, huh? So, hop on. The spaceship of knowledge is lifting off. Your first stop is 2.5 billion light years away from Earth. It's a quasar, one of the brightest objects in the universe and the first one to be discovered. A quasar isn't a star, but a distant galaxy. This extremely bright object gets its power from a supermassive black hole. A disk of matter swirls around the black hole and creates friction. It's kind of like when you're cold and rub your hands together to stay warm. The friction between the palms creates heat, making you feel nice and cozy. The same happens in the quasar, just the amount of heat is bigger, way bigger. I hope you remember to pack sunscreen lotion. The temperature at the heart of this quasar can reach 18 trillion degrees Fahrenheit. Also, there is light, a lot of it. This celestial object shines 100 times brighter than all the stars in its galaxy put together. Well, it's time to cool down a bit. Minus 457 degrees Fahrenheit, to be precise. This is the temperature of a young planetary nebula called the Boomerang Nebula. It sits 5,000 light-years away from Earth. NASA's Hubble telescope caught images of the formation in 1998. It's composed of gas coming from a star near the end of its life cycle. Inside the nebula, it's windier than in the Windy City. Winds reach speeds up to 310,000 miles per hour. And you gotta thank them for the nebula's chilling temperatures. Researchers were just impressed to find out that the temperature of the Boomerang Nebula is just 1 degree above absolute zero. 0 Kelvin should be the coldest temperature possible. This is the point where all molecular and atomic activity stops. Brr! Makes you want to crank up the thermostat in your spaceship. Next, you're going to a place you might not want to visit. Sorry. So, it's the most massive black hole. This giant is located at the heart of a large galaxy, some 10.4 billion light-years from our planet. Its mass is 66 billion times greater than that of the Sun, enough to make our galaxy's supermassive black hole feel ashamed. It has a mass of merely 4.5 million times that of the Sun. But you better not get near any of them, as a black hole's diet consists of matter. By calculating how much matter they consume, scientists can determine their rate of expansion. And those black holes have quite an appetite. Astronomers believe there are stupendously large black holes, or slabs, hiding somewhere in the universe. If they're real, their mass is estimated to be greater than 100 billion times that of the Sun. Now, it's time to snack on something lighter. The spaceship enters the Kepler-51 system. It's home to the lightest planets in the known universe, called superpuffs. Sounds fluffy enough, and it is. These planets' mass is either the same or slightly greater than that of Earth. But this doesn't mean they're small. Think of them as giant cotton candies the size of Jupiter. They are newly born planets whose atmosphere is still cooling down. You might want to wait for this process to be over, though, as 500 degrees Fahrenheit is too hot to handle. But for experts, superpuffs are special. These planets are incredibly rare, as they've managed to discover less than 20 so far. Now, are you up for a race? Let's say the ship you're on is traveling at a speed of 25,000 miles per hour. This is the current human speed record. It was set by NASA's astronaut trio from the Apollo 10 mission in 1969. And no, I am not talking about Neil Armstrong and Buzz Aldrin. That was the Apollo 11 mission later that year. Right now, you're going to race against a star 18,000 light-years from Earth. Your biggest advantage is that this is a neutron star. It was formed when another massive star ran out of nuclear fuel and couldn't support itself anymore. Think of a car running on an empty tank. Victory couldn't be any closer, right? Well, not quite. When a massive star feels like its time is up, it shrinks and starts spinning. Figure skaters do the same during a spin. They fold in their arms to increase rotation to the maximum. This neutron star is the champion of the universe. It spins at a speed of 157 million miles per hour. That's roughly 27% of the speed of light. Whoa! Are you running low on energy at this point? Time to charge up from a gamma ray burst. Gamma rays are electromagnetic waves generated by various forms of radiation. These bursts were fairly unknown to science until the late 1960s. Satellites equipped with gamma-ray detectors accidentally recorded huge outbursts of radiation outside of our solar system. What were they? Nothing dark, definitely, as these are the most energetic forms of light. Scientists believe that gamma-ray bursts happen when two neutron stars collide and form a black hole. The other explanation is that they are in the final stage in the life of a supernova. This event happens when a star decides to go out with a bang. Gamma-ray bursts shine brighter than a diamond. They are 1,000,000 trillion times brighter than the Sun. Talk about an energy boost. Your mood is lightened up by now. You want to visit a place that has a draw to it. No, it's not a beach resort, but a magnetar. It's a neutron star with a twist. Magnetars have a magnetic field that is 1,000,000,000,000 times stronger than that on our planet. But don't fall for their strong appeal. Let's just say you won't live to tell a tale if you get too close to one. In 2004, a flare that came off the surface of a magnetar managed to compress Earth's magnetic field from a distance of 50,000 light-years. Quite impressive for a star the size of a city. Makes you wish to team up with this oversized magnet to commit the greatest heist ever. A magnetar has the ability to swipe all the credit cards on planet Earth from a distance halfway to the moon. Luckily for humans, NASA has discovered only 31 of these stars so far. You have barely escaped the pull of a magnetar. Suddenly, you start to sense a strange force drawing you away from your home base. It is the Great Attractor, one of the biggest mysteries of the universe. This massive gravitational irregularity has been pulling us closer and closer to it for billions of years. Scientists estimate that the Great Attractor is located at the center of the Laniakea supercluster. The name means immeasurable heaven in Hawaiian. It represents a gigantic collection of planets, stars, and asteroids. Our home galaxy, the Milky Way, is just a speck in this enormous supercluster. According to the Big Bang Theory, not the TV show, the real theory, the universe has been expanding in all directions. But the mysterious Great Attractor is slowing things down. How exactly? Researchers still need to figure this one out. On the bright side, they are good at naming things. The end of the universe would be called the Big Crunch, if there's anyone left to call it that. Your journey, too, ends at the edge of the universe. The most distant galaxy from Earth is the oldest one as well. The galaxies that formed first after the Big Bang have drifted the furthest. So every time advanced telescopes detect a far, far away dot, they give scientists an image of the origins of the universe.
There's this mysterious thing in space, an unusual spot that scientists haven't been able to explain for more than 15 years. There are different theories, and one of them says that maybe this is an imprint from a collision with a parallel universe. Is this true? Well, let's see. Take a look at this map. This is the map of our universe. Well, not really. This is actually the map of cosmic microwave background radiation, or simply CMB. Many, many billions of years ago, there was a Big Bang. It was so powerful that it created our entire universe. And, of course, such an event couldn't occur without leaving some consequences. And these consequences are literally everywhere. The Big Bang left electromagnetic radiation, which we know as CMB. We don't notice it in our daily lives, but it's literally here, under our noses. And if you had some kind of superhuman vision, you would see how everything around you shines with this dim light. This radiation is very important. If we hadn't discovered the CMB, we would never have found out about the Big Bang. Previously, scientists believed that the universe had always existed. There was no beginning and there was no end. It sounded pretty ridiculous to us now, but less than a century ago, people were absolutely sure of it. Stephen Hawking was one of the first scientists to guess that the universe did, in fact, have a beginning. The guy was so cool that he realized this as a student while working on his doctoral dissertation. But unfortunately, he had no proof. If there was such a strong bang billions of years ago, then where are the traces? Where's the proof? Laughed people who believed in the eternal static universe theory. But don't worry, they had the proof rubbed in their faces real soon. In 1965, astronomers Arno Pienzas and Robert Wilson discovered CMB, and that was the first grandiose proof of the Big Bang. It turned out that radiation was everywhere. We just didn't notice it. In fact, at first, Pienzas and Wilson themselves mistook it for the noise of a big city, or pigeons, or something else. For their discovery, which turned the world of science upside down, they received the Nobel Prize. Alright, so people learned that they were surrounded by electromagnetic radiation. Then they started collecting more data about it. They accumulated more and more info over the years until they made this very map. This is a map of CMB temperatures. But while creating it, scientists discovered something unusual. Let's take a look at this map. It looks like a large and diverse pattern of cold and warm places. But in reality, our universe is quite uniform. All temperatures on this map are close to negative 455 degrees Fahrenheit with very little difference. All temperature fluctuations between these places are small, and each tiny speck actually spreads over millions of light years. so everything in our world is pretty calm and stable, except for one point. This cold spot right here. Astronomers first discovered it in 2004. First, it looked like nothing unusual. It's just a region where the temperature is below average for a couple of microkelvins. But remember, we're not talking about a small area. This is a giant cold region. It's literally billions of light years in size. Wait, the scientists thought, this can't be true. The universe should be consistent everywhere. According to our standard model, this cold spot simply shouldn't exist. But it does exist though. This isn't just some mathematical error, it's right there. So what is this cold spot, and how did it appear? Astronomers have been trying to find the answers to these questions for years. Even now, we have only a few theories. So let's discuss them all. Theory 1. Cosmic texture. This idea was brought up at the end of 2007. Then scientists suggested that this cold spot could be the hills of space. In other words, it may be a bumpy region of the universe, just part of its texture. But that's a silly explanation, so this theory was quickly discarded. Theory 2. The supervoid. This hypothesis was considered the most plausible for a while. It stated that the cold spot was actually the so-called supervoid. It's a terrifying, dark place of our universe with almost no galaxies. And because it's an empty region with almost no stuff in there, it seems cold to us. However, this theory was refuted in May 2017. After carefully examining the cold spot, scientists found out that there were no signs of a supervoid there. Moreover, voids and supervoids, which actually exist by the way, are still very small in size. The cold spot is literally thousands of times bigger than them, so there must be some other explanation. And there is one, perhaps the most bizarre of them all. Theory 3. A parallel universe. This controversial idea was put forward by cosmologist and theoretical physicist Laura Mersini-Houghton. She suggested that the cold spot could be an imprint from the collision of our universe with a parallel one. Standard cosmology cannot explain such a giant cosmic hole, says Mersini-Houghton. This is the unmistakable imprint of another universe beyond the edge of our own. Her assumption is based on the theory of the multiverse. This theory says that there's actually an infinite number of universes like ours in the world. They constantly collide with each other, giving each other a push, which creates a new Big Bang. So maybe the cold spot is a bruise from such a collision. For quantum mechanics, such crazy theories are pretty common, but for standard physics and our simple understanding of the world, this is earth-shattering. Of course, we need strong evidence. And Mersini-Houghton's team has begun to work on it. Professor Tom Shanks from the Center for Extragalactic Astronomy at Durham University also participates in this research. The craziest sounding of the exotic models for the explanation of the cold spot, the multiverse is actually the most standard in terms of our current model of the universe, he wrote in one of his works. So, what evidence do we need? Well, our cold spot is located in the southern hemisphere. According to Shanks, if there really was a collision between two universes, we should find another cold spot, and it should be in the opposite northern hemisphere. If astronomers actually found it, this theory would be confirmed, and it'd become the first proof of the existence of a parallel universe. But it's not that easy. To find a second spot, we need the latest, highly sensitive telescopes. We also need to find out some info about the nature of dark energy, how it affects space, and, in other words, there's still a lot of work to do. Not so long ago, scientists actually believed they had discovered the second spot. Researchers from New Mexico thought they had found it in the northern hemisphere. But unfortunately, this is likely to be a mistake. The map these researchers used had a high measure of randomness, so it's possible that their discovery is just an accident caused by other voids. So, basically, we haven't found another cold spot so far despite careful analysis. But again, even the best modern equipment is not perfect, and it doesn't mean that there's no second spot. It just means that we haven't found it yet. But if one day we did find it, it could change the world of science forever. We'd confirm not only the theory of parallel universes, but also the famous string theory. It could explain everything that occurs in our world. But if this happens, we'll get even more questions than we already have. How did these two universes collide? How does it all work? So far, it's all just guesswork. We can't claim that the cold spot is a print from the collision of parallel universes. But we can't refute this either. Actually, we may never know the truth at all, but it's still interesting to strive for it. Jupiter is the largest planet in the solar system. More than 1,300 Earths could fit inside this gas giant. It's also 2.5 times more massive than all the other planets of the solar system combined. But if you think this is mind-boggling, I've got some great news for you. Very recently, a team of astronomers have discovered a much bigger planet with the help of the Subaru telescope and the NASA Hubble Space Telescope. It's a Jupiter-like protoplanet orbiting a very young star, AB Aurigae. The star is probably still forming and is no more than 5 million years old. For comparison, our Sun is 4.6 billion years old. The young star is located at around 531 light-years away from Earth in the constellation of Aurigae. The star is shrouded in a thick, quickly moving layer of gas and dust. This disk feeds the growth of the star. Later, what's left of the disk will come together to form the elements of the planetary system. Planets, dwarf planets, comets, asteroids, you name it. But back to the newly discovered planet. It's a gas giant whose mass equals that of 9 Jupiters. Can you imagine this colossus? It takes the planet, named AB Aurigae B, almost 588 Earth years to complete just one journey around its parent star. Maybe because it's 93.9 AU, astronomical units, away from it. Now, why is the discovery of this planet so amazing? Because according to astronomers, it's been forming in a very bizarre way. Or should I say, is forming, since this gas giant is still in the process. Anyway, the unusual thing is that AB Aurigae B is coming together as a result of a top-down gravitational collapse of giant clouds of gas. But scientists say that a much more common model of planetary formation is when dust and rocks gradually accumulate around some kind of core. This proves the idea that there are numerous ways for planets to form. It can also mean that there probably are very diverse planetary systems in our home Milky Way galaxy. But AB Aurigae B isn't the largest exoplanet ever discovered. In 2005, astronomers spotted a mysterious space body. Later, they called it GQ Lupi b. The thing was orbiting a young star at a distance 2.5 times greater than that between the Sun and Pluto. Scientists came to the conclusion that the object was either a planet or a brown dwarf, which is basically a tiny star. If astronomers decide that GQ Lupi b is a planet, it will be the largest ever found, with a radius that is 3.5 times that of Jupiter. The biggest star we know about is called UY Scuti. This hypergiant has a radius that is about 1,700 times greater than that of the Sun. If you somehow manage to place UY Scuti in the center of the solar system, its edges would stretch far beyond Jupiter's orbit. As for the dust and gas streaming from the star, all this would extend beyond the orbit of Pluto. That's 400 times the Sun-Earth distance. A black hole is a spot in space where the pull of gravity is so strong that even light can't escape it. But why is gravity so powerful there? Because matter is squeezed into a teeny tiny space. Supermassive black holes, which can be many millions of times the mass of the Sun, tend to lurk in the centers of galaxies. The most massive black hole astronomers have discovered so far is TUN 618. Its mass is equal to that of 66 billion suns. It was the year 2010. With the help of the Fermi telescope, astronomers spotted something ginormous, something entering the Milky Way. Their discovery looked like massive blobs of matter that could only be observed in particular wavelengths of light. They were also about 25,000 light-years tall. Scientists think that the blobs, called Fermi bubbles, could be produced by our galaxy's central black hole. Space seems to be extremely deserted, but some places are even emptier than the rest, like supervoid in Eridanus. Astronomers noticed this huge region of empty space in 2004. The area stretches 1.8 billion light-years across. It's mysteriously devoid of gas, dust, stars, and even dark matter. A nebula is a massive cloud of gas and dust floating in space. Some nebulae form when a star is nearing the end of its life and throws out loads of gas and dust. Others appear in regions where new stars are forming. The largest nebula we know about is the Tarantula Nebula. In its longest span, it measures over 1,800 light-years. This nebula, also known as 30 Doradus, is located around 170,000 light-years away from Earth. Unlike its namesake, the tarantula isn't dangerous. Quite the opposite. It's a stellar nursery, which means it's a region where tons of young stars are born. Even cooler, it's the most active star-forming area in our entire galactic neighborhood. In 2021, the biggest ever comet we know about entered our solar system. It was 85 miles across, and its icy nucleus was 50 times greater than the nucleus of the previous record breaker. The intruder's mass was a whopping 100,000 times bigger than that of the average comet. In fact, C 2014 UN 271 Bernardinelli Bernstein was so large that astronomers first classified it as a minor planet. Is it going to crash into Earth? Nah. It won't get closer than 1 billion miles to our beautiful green planet, and it won't happen until 2031. But could there be comets even bigger than that? Who knows, but the thought is terrifying. There are loads of bizarre things in the universe, and hypothetical nuclear pasta is one of them. If it does exist, nuclear pasta is the strongest material in the entire universe. It forms from the leftovers of extinguished stars when this substance gets squeezed into spaghetti-like tangles of material. It can theoretically break, but only if you apply 10 billion times the pressure needed to shatter steel. Pulsars are spherical space objects the size of a large city, but they pack more mass than the entire sun. They radiate 2 narrow beams of light, sending them in opposite directions. The Black Widow pulsar, just like its spider namesake, is munching on its partner. It's a lightweight brown dwarf star. The more material the pulsar consumes, the more slowly it spins. The energy the neutron star is losing in the process causes its companion star to dwindle. Haumea is a dwarf planet orbiting the Kuiper Belt. It's a donut-shaped ring of objects around the Sun that extends just beyond the orbit of Neptune. The mini-planet has a bizarre, elongated shape and 2 moons. The day on this planet lasts just 4 hours, which makes it the fastest-spinning large object in the solar system. But the most mysterious thing about Haumea is that the planet has a thin, 40-mile-wide ring circling it. What is it? Where did it come from? No one knows. Could be the result of a collision that happened in the distant past. The 18th brightest star in the night sky, Fomalhaut, is a terrifying sight. It's dubbed the Eye of Sauron because it looks like a ring of dust and debris circling it. It makes the star look like a giant eye staring into your soul. The intimidating star is more than twice the mass of the Sun. It's 25 light-years away from Earth which isn't that far away considering distances in space. Look at this butterfly. Its wingspan is more than 3 light-years, and the structure inside this nebula is one of the most complicated ever observed. The nebula's central star, a white dwarf, is heated to an incredible 450,000 degrees Fahrenheit. It means it was formed from another gargantuan star, more than 5 times the size of the Sun. The white dwarf is surrounded by a thick disk of dust and gas at the equator. That's what probably makes the whole structure look like an hourglass or a butterfly.